Bismillahirrahmanirrahim.
My dear students, I am Dr. Muhammad Yasin from University of Education, Raslabad campus. Today we are going to discuss purification of water-soluble natural products. So our emphasis will be on the isolation of the natural products that are soluble in water. Here is a list of key concepts that we are going to learn today in this lecture. First of all, we will go into the introduction of the isolation of natural products that are soluble in water. We will then discuss the general extraction procedures for the water-soluble products. We will also discuss the desalting and the choice of buffer solutions for the extraction and purification of water-soluble natural products, and in the last we will discuss how a chromatographic sport is selected for the separation of water-soluble natural products. So this is all about the today's lecture. Isolation of compounds in pure state from natural sources is the most important, yet can be difficult and time-consuming step in natural product research. It begins with the process of extraction followed by various separation techniques. One such separation technique is the solvent partitioning method, which usually involves the use of two invisible solvents in a separating funnel. In this method, compounds are distributed in two solvents according to their different partition coefficients. This technique is highly effective as the first step of fairly large-scale separation of compounds from crude natural product extracts. In this lecture, the generic protocols for the separation of the water-soluble natural products will be discussed step by step. Recent advancements in separation and structure elucidation methods have been remarkable. It is not unusual for some micrograms of substances to be purified from vast amounts of biological materials and their structures elucidated. The major contributing factors are progress in high-performance chromatographic technique and computer-aided high-resolution nuclear magnetic resonance, that is also called abbreviated as NMR. With the help of these two techniques, a number of minute biologically important substances have been brought to light which would have been inconceivable a few decades ago. Despite all this, the purification of small water-soluble molecules is still shunned by most researchers. For example, a glance at the natural section of chemical abstracts shows that about 95% of new substances reported are in lipid-soluble category. There may be more lipid-soluble compounds than water-soluble compounds in nature, but the ratio seems to be greatly disproportionate. Clearly, this reflects the difficulty in purifying small molecular weight water-soluble compounds. About 10 years ago, some authors wrote a guide for the purification of marine natural products with the emphasis on water-soluble compounds. So in this lecture, we are going to discuss the methods that can be used or the general procedure that can be used for the extraction or purification of water-soluble small molecules. So with the exploration of marine, more and more plants are being added into the catalog, and hence people are separating new and new water-soluble natural products from the marine plants as well. In line with the principle like dissolves like, one might think that the most suitable solvent for the extraction of water-soluble compounds is water. More often than not, however, simple maceration of fresh biological material with water or aqueous buffer fails to extract water-soluble compounds because they are mostly stored in protected states. The mechanism of such protection is varied. For example, some Water-soluble small molecules are bounded to the membrane, some are stored in specialized compartments, some are protected by the lipophilic materials, and so on. This problem is usually not encountered in the extraction of lipophilic compounds because organic solvents break up the compartmental structure. For that reason, polar organic solvents such as methanol or ethanol are often used in the extraction of water-soluble compounds even if they may not be best solvents to dissolve the target molecules. Also, these organic solvents are much easier to evaporate than water. Other methods to break up the compartmentalizations are sonication, freezing, thawing, freezing drying, heating, and enzyme digestion. These methods can be used singularly or in a combination fashion. Use of organic solvents also prevents microbial growth. That is one of the most serious problems associated with the isolation of organic water-soluble compounds. This slide is the repetition of what I have informed you in the previous slide. In the previous slide, I have told you that in the majority of the plants, water-soluble compounds are stored inside the lipophilic compartment. So the use of the polar organic solvents works both for dissolving the lipophilic compartment as well as for the extraction of water-soluble compounds by making hydrogen bonding. Also, methanol and ethanol are easy to evaporate than the water. Other methods used to break the lipophilic compartments include sonication, freezing, thawing, freezing, drying, and enzyme digestion. So one can use any one of these methods for the breaking of the lipophilic compartments, or one may also apply more than one method for the extraction of water-soluble molecules from the lipophilic compartments. Use of organic solvents also prevents microbial growth, one of the most serious problems associated with the isolation of water-soluble compounds. It is imperative that all isolation work be done in a cold room. Use of antimicrobial agents such as sodium azide has sometimes been recommended. But I personally do not recommend the use of alkaloids during the isolation process because there is a strong evidence that the azides can react with the certain molecules to form triazo derivative. So if you are sure that your natural products do not react with the sodium azide, you may use the sodium azide. If azide is used for the preservation of gel columns or other spores, care should be taken to wash it out thoroughly before use. Another problem associated with aqueous system is the activation of enzymes such as peptidases, glucosidases, sulfatases, and oxidases by solubilization. If the desirable compounds are susceptible to enzymes, the native natural product will not be isolated. A well-known example is the digitalis cardiac glucosidase. The genuine glucosidase are purpurea glucoside A and purpurea glucoside B. In the normal extraction process, it is difficult to isolate the native glucosidase because the terminal glucose unit is lost by the action of indigenous beta-glucosidase, and only digitoxin and G-toxins can be isolated. Deactivation and denaturation of the enzyme can be carried out by quick heating or treatment with alcohol. But alcohol treatment does not necessarily deactivate the enzyme. Therefore, it is strongly recommended that the large molecular weight fractions containing liberated enzymes be removed as quickly as possible by methods such as ultrafiltration or gel filtration. Desalting as the choice of the buffer solution. Desalting is probably the most important step in the handling of water-soluble compounds. It is not necessarily difficult to fractionate the water-soluble compounds to a single chromatographic peak. In fact, strongly hydrophilic compounds are routinely analyzed on high-performance liquid chromatography, that is the HPLC, without any trouble. However, what makes the preparative separation of water-soluble compounds so difficult is the separation of inorganic salts, often from minute amounts of the target molecules. This is the step in which organic chemists may simply give up their efforts, since most of them are used to removing inorganic salts by simple partition between the water, immiscible organic solvents, and aqueous solutions. If the compounds have some lipophilicity, the standard method for desalting is the use of reverse phase columns such as C18 silica gel or various other organic polymers such as H3D2, 4 or 7. Usually the aqueous solution is passed through the column and the salts are washed out with water. Subsequently, the organic compounds are eluted with a solvent system containing organic solvents. This method cannot be applied to strongly polar or ionized compounds such as polar amino acids or sugar. Another commonly used method for desalting is the use of side exclusion columns such as Cefadec G10 and Biogel P2. Inorganic ions are presumed to be smallest in the mixture and hence their elution should be expected to be retarded the most. This, however, is not always the case because there are some unpredictable interaction between the compounds and column spores, such as that the predicted elution order can often be reversed. These interactions can hold advantages for the extractor and can be used to isolate the specific type of compounds. For example, I am going to discuss such example in which the extractor have purified a specific natural product from this type of interaction by taking the advantage of this type of interaction. The purification of paralytic shellfish toxins such as saxitoxin and goniotoxins was used by taking advantage of their specific absorption on Biogel P2 and Cefadec G10. In most cases, the extraction and fractionation of the water-soluble compound necessitates the use of buffer solution. After all is said, the key to the isolation of water-soluble compounds is finding suitable pH and ionic concentration to keep the molecules as individual molecular entities separatable on a given matrix. However, the separation of the buffer salts from the compounds is not an easy task. Several volatile buffers have been suggested to avoid this problem. These buffers are mostly the combination of weak bases and weak acids which are bound only by weak ionic interaction and are volatile under reduced pressures or lyophilization. However, in reality, these buffers are not so easy to handle. For example, the organic buffer containing pyridine and other aromatic bases have intolerable noxious odors and are difficult to use in a closed cold room. They also may not be acceptable in the modern laboratory for safety reasons. They also retain lipophilic nature and interact with the fluid just like alcohols. Ammonium acetate and ammonium carbonate buffers are removed by evaporation or lyophilization, but in practice these are not so easy to evaporate. The first lyophilization often results in a sticky mixture of ammonium acetate or carbonate and solutes. Sometimes this process has to be repeated several times. It is usually necessary to redissolve the residue in large amounts of water, freeze and lyophilize again. In other cases, one has to expect drastic pH changes during evaporation which may affect the desired molecule. So in the previous slide, I have discussed about the use of the buffer solutions for the separation of the water-soluble natural products. What kind of buffer solutions are used today for the isolation of water-soluble natural products? Mostly people are using ammonium bicarbonate based buffer solution that has a pH range of 5 to 7, Some are using ammonium acetate buffer solution that have a pH range of 7 to 8. Some others are using a mixture of pyridine and acetic acid based buffer solution that has a pH range of around about 3. Similarly, some are using a mixture of pyridine and acetic acid that has a pH range of 5. There are some reports for the use of a buffer solution that is based on the mixture of pyridine, acetic acid and alpha picoline that has a pH range of 8. Some other have reported the use of a buffer solution that has a mixture of pyridine, acetic acid and 2,4,5 polydine that has a pH range of 8.3. Some other have used use a buffer solution that has a mixture of pyridine, acetic acid and an ethyl morpholine that has a pH of 9.3. So the majority of the buffer solutions that have been utilized for the separation of water-soluble natural compounds utilize the pyridine, and all of you know that the pyridine have a very foul smell that cannot be tolerated in a cold closed room. So this is a main problem during these isolation or purification of the or the extraction of the water-soluble natural products. Without the help of some kind of chromatographic method, the purification of water-soluble compounds would be difficult to accomplish. There are a variety of column packing materials with many choices of interacting functional groups. The interaction of the functional groups of the chromatographic spores with the eluting water-soluble molecules include weak, moderate, and strong anion and cation exchange, ligand exchange, reverse phase, and ion and size exclusion interactions. Here, special attention must be paid to the possible irreversible absorption of certain substances onto the chromatographic spore. We all know well from our experience that the recovery of substances from chromatographic column is rarely 100%. Some compounds tend to disappear on the column. In case of water-soluble compounds, this tendency is greatly enhanced, especially with silica gel-based spores. Some compounds, including amino acids, are virtually impossible to separate preparatory on silica gel-based spores. The mechanism for such irreversible retention is not fully understood, but trapping by hydrogen bonding in suitably shaped pores or matrices may be greatest contributing factor. For some compounds, covalent bonding by microaddition or hemicidal formation is also suspected. With respect to irreversible absorption, there seems to be a strong relationship between the shape of the molecule and the pore size of the chromatographic spores. For example, linear polycyclic ether gravitoxins are easily trapped in silica gel 60 and never eluted even after washing with very polar solvents. The utilization of used silica gel of large pore silica gel can lessen this irreversible absorption, but it also results in pore separation. Similar observations were made with some cyclic peptides. Use of material with larger pore size is sometimes helpful. Material based on a range of silica gel having a different pore size are available commercially. For example, EM Corporation sells silica gel based columns of pore size up to 1000 angstrom. Needless to say, however, the larger the pore size, the smaller the surface area and consequently the lower the number of theoretical plates. Capping of 3 hydroxyl groups on the silica gel helps to prevent the undesirable absorption, and many such end-capped silica gel-based HPLC columns are commercially available. Soft chromatography or elevated temperatures can also help to improve the recovery, but often the problem still remains. Fortunately, C18 and other reverse phase columns which could be used for the separation of water-soluble compounds with greater success are now widely available. They include matrices such as polystyrene and divinyl benzene and hydroxyethyl methacrylate, dimethylacrylate copolymers with various functional groups. Recovery rates are generally much better on these polymeric materials and are accompanied by much longer column size. Before 1950s, water-soluble natural products isolated were mostly limited to molecules that are stable in strongly acidic or basic conditions. In case of amphoteric compounds such as amino acids, a combination of strongly acidic and basic ion exchange reagents can easily separate them from other components. The procedure, however, is not applicable for esters and other acid or alkali-liable compounds that do not survive in extreme pH conditions of the reagents and or buffers. Epimerization of chiral centers can also be a problem. Thus far, an unknown compound or fractionation scheme involving any drastic conditions should be avoided. The most common problem with the resin-based column is the leaching of the resinous material. Even well-washed resins leach small amounts of the organic matter, that's oligomers or degraded polymers, and a strong solvent means an increasing amount of the leaching material. Use of a stronger solvent, for example, dichloromethane, also results in the softening and swelling of the resin. Here, extreme care has to be taken to prevent the breakage or clogging of the column. When a strong organic solvent is applied, it is advisable to use an extremely slow elution speed to prevent the rapid extension of the volume. It is strongly recommended to clean the resin before use, with exceptions like pre-washed XAD2 for pesticide analysis. All commercial resins need pre-cleaning. First, the resin should be soaked in the water in a beaker and small particles must be removed by decantation. This process is especially important because the small particles drastically slow down the solvent speed. The commercial resins are supposedly prepared in certain range of mesh size, but friction during transportation and spontaneous cracking of these produce finer particles. Regarding the breakage of the particles, it is important not to dry the resin. The resin should always be kept moist with either water or methanol. The resin should be washed thoroughly with water or methanol and the solvent that one wishes to use. The use of the soft extractor is also a choice to wash the resin efficiently. Before use, the resin should be washed well and equilibrated with water to make it completely free from the organic solvent. When washing or equilibration is done in a column, the water elution speed of about 10 times of the resin volume is recommended. When the resin is to be put directly into the ongoing fermentation medium, it has to be autoclaved first. Most non-ionic resin can withstand a high temperature, approximately 180 degrees centigrade, well above the sterilizing temperature, which is about 120 degrees centigrade. It should be noted that it is not the case with the functionalized resins like strongly basic or acidic ones. Recent advancements in separation and structure elucidation methods have been remarkable. It is not unusual for sub-micrograms of substances to be purified from vast amounts of biological materials and their structures elucidated. The major contributing factors are progress in high-performance chromatographic techniques and computer-aided high-resolution nuclear magnetic resonance, that is also called abbreviated as NMR. With the help of these two techniques, a number of minute biologically important substances have been brought to life which would have been inconceivable a few decades ago. Despite all this, the purification of small water-soluble molecules is still shown by most researchers. For example, a glance at the natural section of chemical abstracts shows that about 95% of new substances reported are in lipid-soluble category. There may be more lipid-soluble compounds than water-soluble compounds in nature, but the ratio seems to be greatly disproportionate. Clearly, this reflects the difficulty in purifying small molecular weight water-soluble compounds. About 10 years ago, some authors wrote a guide for the purification of marine natural products with the emphasis on water-soluble compounds. So in this lecture, we are going to discuss the methods that can be used or the general procedure that can be used for the extraction or purification of water-soluble small molecules. So with the exploration of marine, more and more plants are being added into the catalog, and hence people are separating new and new water-soluble natural products from the marine plants as well. Now I am going to discuss one example for the isolation of water-soluble molecules from an animal. The method involves first of all, the live newts, about 14 grams or 112 bodies were frozen in a liquid nitrogen and stored before extraction. The animal bodies were means extracted in a homogenizer with a threefold volume of 0.1% acetic acid in methanol for 4 minutes, and then it was centrifuged. The residue was re-extracted twice with a twofold volume of the same solvent. The combined extract was centrifuged, and the supernatant was evaporated to about 500 ml, at which no methanol was left in the solution. After removing the precipitates by centrifugation, the supernatant is diluted with 1 normal acetic acid to 1000 ml, and it is subjected to ultrafiltration. With respect to irreversible adsorption, there seems to be a strong relationship between the shape of the molecule and the pore size of the chromatographic spores. For example, linear polycyclic ether gravitoxins are easily trapped in silica gel 60 and never eluted even after washing with very polar solvents. The utilization of used silica gel of large pore silica gel can lessen this irreversible absorption, but it also results in pore separation. Similar observations were made with some cyclic peptides. Use of material with larger pore size is sometimes helpful. Material based on a range of silica gel having a different pore size are available commercially. For example, EM Corporation sells silica gel based columns of pore size up to 1000 angstrom. Needless to say, however, the larger the pore size, the smaller the surface area, and consequently the lower the number of theoretical plates. Capping a free hydroxyl group on the silica gel helps to prevent the undesirable adsorption, and many such end-capped silica. Desalting as the choice of the buffer solution. Desalting is probably the most important step in the handling of water-soluble compounds. It is not necessarily difficult to fractionate the water-soluble compounds to a single chromatographic peak. In fact, strongly hydrophilic compounds are routinely analyzed on high-performance liquid chromatography, that is the HPLC, without any trouble. However, what makes the preparative separation of water-soluble compounds so difficult is the separation of inorganic salts often from minute amounts of the target molecules. This is the step in which organic chemists may simply give up their efforts since most of them are used to removing inorganic salts by simple partition between the water, immiscible organic solvents and aqueous solutions. At the end of this lecture, here is a list of recommended books. You may consult any one of these books. Thank you very much.